This paper is FADE, Fair Double Ensemble Learning for Observable and Counterfactual Outcomes. FADE is an ensemble learning framework for building fair and accurate predictors. Within this framework, you can build a new predictor from scratch, improve the fairness or accuracy of an existing benchmark predictor, and efficiently explore fairness, accuracy, and fairness trade-offs. Double here refers to several things. We optionally build fair predictors in two stages, first learning a set of base predictors and then ensembling them. We use doubly robust estimators, which also appear in the literature under the heading double machine learning. We handle both counterfactual and observable fairness and performance criteria. And finally, we combine in-processing and post-processing. FADE is simple and flexible and has a novel combination of properties. First, most existing methods are designed for strictly observable fairness criteria. As mentioned above, FADE can target either observable or counterfactual fairness criteria. Second, many methods are designed to target specific fairness criteria like demographic parity or equalized odds, and they don't necessarily generalize easily to other criteria. FADE can simultaneously target a large number of fairness criteria of a very general form. Similarly, many methods are designed for specific model classes. Since FADE is an ensemble learning method, it can combine arbitrary models or basis functions. Fourth, FADE allows you to combine existing and new predictors, so in a sense, it collapses the distinction between in-processing and post-processing. Fifth, many methods are computationally intensive, but FADE yields closed-form solutions which are very quick to compute. And finally, many methods are supported by empirical results, but we provide theoretical guarantees, including fast convergence rates. Here's an application of FADE in practice to improve the COMPAS recidivism predictor. We use 5 base learners, and we use 3 different penalty terms to simultaneously target 3 different fairness criteria. We computed 1,331 different ensemble predictors with different unfairness penalty weights lambda, and we then estimated their performance on a test set. This whole process took around 15 seconds on my 2013 laptop. Here we show the results for 2 of the 3 fairness metrics. Here we're measuring the performance and fairness with respect to counterfactual outcomes. The x-axis is the counterfactual mean squared error, and the y-axis give the difference in counterfactual false positive or false negative rates between black and white defendants. A value of 0 indicates no disparity, and higher values indicate larger disparities. The triangle represents COMPAS, the gray x's represent the 5 base predictors, and the red square represents the least squares ensemble predictor, meaning the ensemble predictor with no unfairness penalties. Each blue circle represents an unfairness penalized ensemble predictor. The majority of the ensemble predictors in blue improve on COMPAS with respect to both mean squared error and fairness. There are many predictors that take the relevant disparity essentially to 0, with very little cost in mean squared error relative to the OLS predictor in red. What about fairness trade-offs? It turns out here that we can effectively jointly minimize all 3 unfairness measures simultaneously. In the columns here, we have the counterfactual mean squared error and the 3 unfairness measures. In the top and bottom rows, we have the least squares ensemble predictor with COMPAS for reference. And here in the middle row, we have the quote-unquote best model, meaning the model that minimizes the L2 norm of mean squared error and the 3 unfairness measures. We see that all 3 disparities can be minimized with almost no increase in loss relative to the OLS predictor, and we can uniformly improve on COMPAS. FADE provides a principled way to explore fairness accuracy and fairness trade-offs in any given problem setting. Thanks for watching, and please check out the full talk for more details.